In this video, we're going to look at linear programming, at least the introduction to it. Much of this material is very important to our textbook by Dixit, and he talks about it in chapter 7 of the text, so you might want to look at that. He's got a small piece in linear programming, but it's important to remember that when we're talking about linear programming, we're talking about something called the simplex algorithm, which we will look into in more detail in the next video. The simplex algorithm has been sometimes referred to as the algorithm that runs the world, and we'll explain that in more detail as we go along. Mathematical programming itself consists of a number of disciplines. First of all, there's concern about algorithms and their mathematical properties. The concern is with theoretical and with computational properties of programming, solution methods, and so on. And then there's the side that I work in most often, is applied mathematical programming, which uses techniques developed by the first group, but it's concerned with solving real-world problems and the specification of problems. It requires specialized computer equipment and particularly software as well. How do you solve these problems? And the interpretation of the solutions, particularly when it comes to shadow prices. And finally, the communication of results to decision makers. So when we talk about general mathematical programming formulations, the general formulation is one where we want to maximize or optimize some function f of x subject to a constraint set. So these are matrices and vectors, so we have more than one constraint, and we find that the constraints are an element of some superset S1, and the solution set is an element of S2, where usually we require, because we're economists, that the x's are non-negative. So linear programming is the most popular and the most common way to deal with these problems, where f of x and g of x are linear and x is specifically non-negative. Then we have nonlinear programming, where f of x and or g of x is nonlinear. Both can be nonlinear, and x again is non-negative. Then there's quadratic programming, where f of x is quadratic and g of x is linear and x is non-negative. Now, the quadratic programming is just a subset, some people feel, of linear programming, because the first derivative of a quadratic is a linear function. And then we have integer programming, where the solution set x takes on an integer. It can be either a 0, 1, or it could be that that x takes on values 1, 2, 3, etc. And that's what we find when we have non-continuous but rather discrete problems. Uses of mathematical programming. While it's primarily prescriptive, suggests practical solutions for solving problems, can be used for prediction, predict consequences of government policies. For example, the Canadian Regional Agricultural Model, the American model. Those are both linear programming models, and sometimes models don't want to be linear, but they have to be because of the size of the problems. I often run linear programming models with over 1 million constraints. Integrated assessment models are sometimes, but not always, a mathematical programming variety. For example, William Nordhaus, who won a Nobel Prize in economics, runs the so-called DICE model, the Dynamic Integrated Climate and Economics model, which is an integrated assessment model that uses mathematical programming. The third use of mathematical programming is sensitivity demonstration. The model reality, validate or calibrate the model, and then look at what-if scenarios. So it's not as if looking at the fourth point, it's not as if such models, that mathematical programming models, lack empirical or statistical input. For example, efforts to calibrate these models use something called positive mathematical programming, which is very much along the same vein as econometric analysis, although it's not nearly as popular because there are questions and it's very difficult to implement in many cases. The coefficients are sometimes estimated using statistical techniques, and these are equivalent to decision variables. So let's start with a motivating example. Suppose we have a poet with a woodlot who needs to earn extra money, and he wants to work no more than 180 days per year. He can earn $90 per hectare per year by managing a cedar forest, or $120 per hectare per year managing a hardwood forest, like a mixed northern forest. He needs 2 working days, which we denote with WD per hectare per year to manage cedar, and 3 working days per hectare per year for hardwoods. Now we can look at the poet's problem, which is going to look like this. We're going to maximize 90 times x1, where x1 is the number of hectares that he's going to put into cedar, plus 120 x2, which is x2 is the number of hectares that are going to go into that he's going to manage for hardwoods. And we see that the left-hand side here is dollars per year, and if we work this through, it should be that the right-hand side is also dollars per year. Now the subject 2's, remember, he only wants to work no more than 180 days. So that's the limit here on the right-hand side. He's got 40 hectares of cedar available to him, 50 hectares of hardwoods, and we've got this non-negativity constraint there. So we can write this as a linear program where we have the objective function Z is 90x1 plus 120x2, which is revenue. We have 2x1 plus 3x2 is less than or equal to 180. That's his time constraint. He's got a cedar area constraint, x1 less than 40, x2 less than 50, and x1 and x2 have to be greater than or equal to 0. The general formulation of a linear programming problem, it looks like this, and this is a standard formula. Z is the objective, equals a vector C times this vector x, so C is a row vector, x is a column vector, subject to A of x, A times x less than or equal to B, so B is a vector, a row vector of a column vector of 180, 40, and 50. X is simply a matrix that has 3 constraints in it, or 3 constraints, so 3 rows, and 2 columns. All right, x1 and x2, and then we have this x greater than or equal to 0. So C and B are parameters, scalars if you like, and x is a matrix, or pardon me, a vector of what we want to solve for, and A is our technical coefficients matrix. Another problem that we might look at is suppose x1 is the amount of mechanical pulp in tons per day, and x2 is the amount of chemical pulp in tons per day that we produce, and each requires 1 work day per ton of pulp produced. We also have a biochemical oxygen demand, which is a measure of pollution, and we assume that 1 ton of mechanical pulp produces 1 unit of BOD, biochemical oxygen demand, and 1 ton of chemical pulp produces 1.5 units of BOD. Revenues from mechanical pulp are somewhat lower than for chemical pulp. There's $100 per ton for mechanical pulp and $200 per ton for chemical pulp. Now we can do a number of things. We can maximize net revenue or revenue if we like. We can maximize employment. All right, we haven't talked about that yet. Oh yes, we have. We've got 1 work day of required per 1 ton of pulp produced. So that's less interesting. or we can minimize the pollution. Now the constraints are that at least 300 workers need to be employed and a minimum revenue of $40,000 per day is required. So we can set this up the same way as we did before as a linear program. So we have, we're going to minimize pollution here. So we have 1 ton of pollutant, or pardon me, of whatever measure BOD is per ton of mechanical pulp, and 1.5 units of BOD per ton of chemical pulp. We also have that employment is 1 times x1, and 1 times plus 1 times x2 has to exceed 300. This is worker days per ton times ton per day, which is the x1 value, and we get worker days per day. Okay, so this is worker days per day. We need a revenue of $40,000, so we have 100 x1 plus 200 x2 has to exceed $40,000. Again, this has to be equal to, so that the dollars per day on the right is equal to the dollars per day on the left. We have capacity constraints, which we haven't mentioned yet. X1 is less than or equal to 300, X2 less than or equal to 200, and X1 and X2 have to be non-negative. Now, in reality, this problem is a multiple objective decision-making problem, but we won't get into that. That's another issue altogether. So again, we can write this in this form. Minimize Z is x1 plus 1.5 times x2. x1 plus x2 has to exceed 300. 100x1 plus 200x2 has to exceed 440,000. x1 is constrained to be less than 300, and the chemical pulp has to be less than or equal to 200, because these are plant capacity constraints, and x1 and x2 have to be greater than or equal to 0. Now, we need to get this into standard form, and the standard form was shown before as C times X in terms of matrices and vectors, subject to AX less than or equal to B. So in order to get it to maximize the problem rather than minimize like we have above, all right, so when we want to maximize, we multiply the left-hand side and the right-hand side by -1, and we get minus x1 minus 1.5 x2. We also do that to the first constraint here. We multiply by -1 in order to get it into the standard form, minus 300. We do the same thing with the second constraint. We have to multiply through, and then these two constraints are in the proper form to begin with, and x1 and x2 have to be greater than or equal to 0. So again, here's our standard form of the LP, where z equals c of x. There are n decision variables, ax less than or equal to b, so we have m constraints, so then x is a m by n matrix. Let me think, yeah, and x is n by 1, b is an m by 1 column vector, x greater than or equal to 0, and we have this result here. X is right here, b m1 here, and this is m times n, where we have all these coefficients. So these are known. These are our technical coefficients that are required for, they're just the technical relationships, and b is a set of right-hand side constraints. All right, what are the assumptions of linear programming? Well, first off, the objectives and constraints are appropriate to the problem at hand. Second, we have proportionality. The contribution of each decision variable to the objective is constant and independent of the variable level. Use of each resource per unit of each decision variable is constant and independent of variable level. There are no economies of scale, so we have constant returns of scale and we discussed that in earlier lectures. We have additivity, no multiplicative or interaction terms, so we don't have an x squared or y squared, no x times y. Decision variables are infinitely divisible, and there is no stochasticity or randomness in these types of models. You can put them in, but that's done in different ways, and we can explore that maybe in another course or maybe later in the course, looking at uncertainty, which is, I think, chapter 9 of Dixit. Okay, then going back to the POET problem, we specify the revenue as follows, and you've seen this already: 2x plus 2x1 plus 3x2 less than 180. That's the time constraint, less than equal to 40 and 50 for the amounts of cedar and hardwood that the POET has available, and we have, again, non-negativity. So we can draw the constraints as follows. So here x1 is your cedar, and this then is 40, and that's our constraint for cedar. The constraint on hardwoods is 50 hectares available hardwoods, and then finally we have this relationship of time, 2 days to have per unit of x1 harvested per hectare, and 3 days for hardwoods. So for cedar, 2 working days, and for hardwoods 3 working days, with total has to be less than or equal to 180. So this is the equation for that. Then we have the objective function, 90x1 plus 120x2. We've got this in blue, and what we want to do is get out on the highest possible blue line that we can. And you'll see that these 2 points here are 40 and 33.3, so 33.3. So if the POET allocates all of his time, or enough time to manage 40 hectares of cedar, then he can only manage 33.3 of hardwoods. If he manages 50 of hardwoods, he can only manage 15 hectares of softwood, of cedar. So you see here's the direction. So we've got some values here: 1800 Z, 3600, and over here 7600. So these two, they don't seem to match. Oh no, I'm getting that confused a little bit here. So you'll see, because of the slope of the line, this is the optimal one. If you take another line, another blue line that's parallel to this one, and these are parallel, then you'll be slightly below, you'll have a lower total income. So let's consider yet another example. A firm produces wheat and canola using tractors, land, and labor as input. And we have input requirements that 2 units of tractor power are required for producing wheat and 1 for canola, and you've got 70 units available. Maybe this is hours per week or hours per season. Land, we have 1 hectare of wheat and 1 hectare of canola are required to meet our canola and wheat requirements, and we have 40 hectares of land. And finally we have 90 days or hours of labor, and we can allocate 1 hour of labor to produce a hectare of wheat, and 3 hours of labor, or 3 days, however we want to measure it, to produce the canola, a hectare of canola. We get $40 revenue from a hectare of wheat, 60 from canola. So by now you should be able to figure out how to set that up. And here's what we do. We have net revenue, which we've denoted with this pi, is 40x1 plus 60x2, where x1 and x2 are the amounts of land allocated to wheat and canola respectively. 2 2x1 plus x2 is less than 70, less than or equal to 70. That's your tractor hours. x1 plus x2 less than or equal to 40. That's the land available in hectares. And x1 plus 3x2 less than or equal to 90 is the amount of labor hours. And again, we have that requirement of non-negativity. So we can set it up as in matrix form. So we have 2, 1, 1, 1, 1, 3. Those are your A, little a values. So A11 is 2, A12 is 1. The right-hand side constraint numbers, we call that the vector B, and that's traditional in LP. And 40 and 60 are our C coefficients up here. And then, of course, X is a column vector of the possibilities. So here we have the three constraints. This is the tractor hours constraint, this is the labor constraint, and this is the land constraint. And you'll see that they intersect at various places. This becomes the feasible region because we have to be below this line, we have to be below this line here, and we have to be below this line here. So this we call the feasible region, which I've marked with these lines. And now I've denoted these points. A is the origin, B is the value up here, this point, C is that point here, and D here, and E. And our solution is going to lie on one of these points. That's the key to linear programming. All right, it's either going to be A, or it's going to be B, C, D, or E. Anything in between is really not that acceptable, but we'll have some caveats with respect to that too. So this is the direction of optimality, and this is the objective function. And we see that the objective function is going to hit that feasibility region right here at point C. And at point C, we have 15 hectares allocated to wheat and 25 to canola. Wheat gives us $40 a hectare and canola $60. Now, in order to represent this problem, and this is what Dixit discusses with us in his text from actually chapter 1 on, but he uses slightly different notation. So in this case, we need slack variables in order to get rid of the inequality constraint. So we have a slack variable here for tractors, slack variable for land, and a slack variable for labor hours. If any of these slack variables are positive in the optimal solution, then the associated shadow price for that slack variable is 0. All right, and that's because of the complementary slackness condition. So that's how we set up the problem, and notice that slack variables don't contribute to net revenue, but we include them in here nonetheless. So we begin with the slack variables set to the right-hand side constraint values. So when we try to solve this problem, we begin with these slack variables set to these values here, and then we try to see if we can move away from that, because clearly if the slacks are all set to those values, then we're at the origin when we begin looking at the problem. Now, we will do that in the next set of lectures, but for now, let's look at duality. For every primal problem, and so far we've constructed primal problems only, there is a dual problem. Solving the primal simultaneously solves the dual. In other words, the dual constitutes these slack variables, and vice versa. So if we solve the dual, we also solve the primal. So there are cases where it's not possible to solve the primal problem, but you can solve the dual problem, and vice versa. If a solution to the primal cannot be achieved, then it may be possible to get a solution by solving the dual instead. For economic applications, the dual variables have an important interpretation as shadow prices. So here again, we come up with these shadow prices to which Dixit devotes an entire chapter. So here is how we compare the dual and the primal. So we begin with the primal. We set revenue equal to C of X. A of X less than or equal to B is our constraint set, and this is the non-negativity set. We maximize. We have a less than or equal to constraint, a greater than or equal to 0, and an equal constraint, and X free. So let's look at that. So the first thing we do is we change maximize to minimize. So we go from max to min. For every less than or equal to constraint, we have a dual variable y greater than or equal to 0. So that if it's a less than or equal to constraint, we have a dual variable that's got to be positive, non-negative. If one of our original variables is greater than or equal to 0, one of our original control variables, then the constraint has to be greater than or equal to 0. The constraint has to have a greater than or equal to sign. All right. If we have an equal constraint, then y is a free variable. In other words, it can take on either a negative or a positive value or 0. And if x is free, so in other words, x is not restricted to being greater than or equal to 0, then the constraint is an equality constraint. So here we've done that. We've taken the revenue, and now we're minimizing cost, where cost is b times y, where y is a vector of dual variables or shadow prices. We have a less than or equal to constraint, and here we have a greater than or equal to c, where c is from here. All right, so the b goes up into there, and the c goes down into here. The variables, because of this, all right, because we have this constraint, then we have, or pardon me, this requirement of non-negativity, so therefore that constraint, this constraint has to be greater than or equal to c. So this is the dual problem. This prime here refers to the transpose of A. So we've transposed the original matrix A. Now, here's an example. So we have net revenue 30x1 plus 45x2 subject to input use less than or equal to input supply. And we've got these three constraints and these two greater than or equal to 0. And that means that our activity levels, these x1s and x2, are greater than or equal to 0. Now, how do we convert that into a dual problem? Well, we minimize. So here we had input use less than or equal to supply. We minimize the cost, where the total cost is given by 15 times this shadow price y1, 10 times shadow price y2, and 0 times the shadow price y3. The shadow prices depend on these particular solutions, right? So in other words, the shadow price for 10 is given by, suppose we make this 11, how does that affect the solution here? All right, suppose that the solution here was 400, all right, that was the maximum net revenue, and we increased this by 1 so that the net revenue increased to 425, then y2 would end up being 25. All right, so you can think of that. So here we have this less than or equal to constraint, then the associated dual variable is positive, or non-negative rather. Here another one less than or equal to, another one less than or equal to. That means that they're all non-negative. because x1 is greater than or equal to 0, we have the constraint that 4y1, 2y2 minus 1y3 greater than or equal to 30, where 30 is up here. And with x2 greater than or equal to 0, we get 3y1, 3 comes from there, 1y2, and 5y3 greater than or equal to 45. And that tells us that the marginal cost must be greater than or equal to the marginal revenue. And think about it. Marginal cost is going up, marginal revenue is going down. In the general sense, they intersect, then we have an equal sign, but it has to be greater than or equal to. And when you solve the problem, unless there are other kinds of constraints in the way, this will be an equality sign when we solve it. The slack and dual slack or surplus variables. So marginal cost greater than marginal revenue in the dual representation. A constraint to the dual problem can be associated with a slack or marginal loss variable, which has the following definition and meaning. So the marginal cost is equal to the marginal revenue plus the dual slack variable. Or we can write that differently. Marginal cost minus marginal loss is equal to the marginal revenue, where the marginal loss is identically equal to the dual slack variable. That is why we subtract ys, the marginal loss, from the left-hand side of the dual constraints in the next diagram. So consider again the problem diagrammed above, where we had tractor hours 70, 40, and again we can represent that in the following way in matrix notation. And the dual slack representation looks like this. So 70y1, 40y2, 90y3, 0y times the slack, 0 times the second slack. Then we have 2 plus y2, 2 times y1 plus y2 plus y3 minus the first slack is equal to 40. y1 plus y2 plus 3y3 minus the second slack is equal to 60. All of these variables have to be non-negative. The variables with the subscript S1 and S2 are the dual slack or surplus variables, and these surplus variables constitute the marginal loss for wheat and the marginal loss for canola, respectively. We will continue that in the next video. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.